So I will use only these three in the weak derivative, and with the help of weak derivative, I will define the definition of Sobolev space, and we will see some example, and we will see some counter example also, and then we will go to the completeness property. So let us start with the weak derivative definition. Sorry, before weak derivative, I will introduce some notation. So let omega be a subset of Rn. I assume every time it is open. And I define a function over it. And I assume that it is a real valued function. So first we will see the Sobolev space, which is real valued, and then we will generalize it to vector valued, but still the theory is same for the vector valued also, because you can do it component wise. And k is any positive integer. Then we have the following notation. The first one, I assume C omega. This is a class of all those function f which is continuous. The second is support of f. I will always take the closure where the function is non-zero. There are some other definition of support which are equivalent to this, but I will consider this. And then the C0 infinity. In the standard textbook, they use C0, but I have studied some Indian textbook also, they use C omega. This C represent the compact support, but I will use C0 omega. So by definition, this is all those functions, they are continuous and the support is compact. The fourth one, Ck omega. All those continuous functions which are k times differentiable.
Hello, Riddhi?
Yes. Hello.
Hello?
Yeah. Hello. Yeah, I can hear you.
What is going on here?
Hello. Any question?
Hello, Amit. Do you have any question?
Can you give some another definition for support web?
Can I,
Or
sorry,
can you
I
give any another definition for support web? Any theoretical definition kind of?
yeah, I can give.
Yeah.
Let me check. So another definition is all those all those space, all those points in omega, such that the Lebesgue measure of the set where function is non-zero, if you intersect with ball. This Lebesgue measure should always be positive. positive, and this will true for every R positive. So I will call this as a support of F. And you can see, you can verify this and this star support definition are same. So here we are talking about with the measure, but this is given by the Lebesgue measure. And this is a topological property because here we are taking the closure. And closure is topology. You have topology. But here there are topology, but not the smallest one. Here also we are talking about balls. So the balls will be in the space, and this is for every, you can make this radius any radius, and you intersect where the function is non-zero. That measure should be positive.
Okay, thank you, Riddhi.
We can see why this is equivalent. I have an exercise problem that these two support are same. So I can upload the solution on the WhatsApp group.
But the
Okay.
second one is not look simpler.
Yeah, second one is not simpler. That's why I didn't introduce it. So this you can see, means you can see by graph that support is the closer of where the function is non-zero. This looks more complicated, but it is useful in many sense. When your domain has a major theoretical property like Lebesgue differentiation theorem, where you have to take the intersection with the domain, then this is more powerful. Okay. So now we go to C0K. This is all those K differentiable function intersection with the compact support. And C infinity is intersection of all CK functions. This is smooth, I will say. We know that we have familiarity with C infinity function. We say generally this is smooth functions. And the last one is C0 infinity. This is C infinity intersection C0 omega. And this I will say compactly supported function. Compactly supported smooth function or test function. Sorry, I don't have space. Okay. So some remark.
Riddhi, just a small doubt. So
Yeah.
in the definition of CK omega, whether we need this kth differentiation of f to be continuous?
K times K. Oh,
Yeah,
sorry.
k time differentiable, and the
K
kth derivative
times.
should be
Oh, sorry. I continuously differentiable.
yeah.
Yeah. Yes. So some remark. As we have seen the support, so the first remark is support can be outside of omega also. The support should not be inside omega. And the first example I have that support of F can lie outside the omega. The let's say the function u defined over a ball, like u of x is equal to 1 minus mod x. So you can see here the support is closed wall. Okay. And the second one is we cannot rely on the smoothness of the curve looking function. So there are some function which looks like smooth, but they are not smooth by definition. So if I take the function fx, which is my x square if the in the positive axis and minus x square, which is the negative, it's look like, okay, this function is so good because this is a polynomial, but no, this is not C2. I wanted to highlight these 2 points, and this is more general mistake people do. And now I will introduce the motivation of weak derivative. So why we try to explore this weak derivative notion? So let omega be a subset of Rn. I always say this is open because we need differentiation, and U is in C1 omega and phi a compact supported function. Then by integration by path, I will shorthand notation integration by part. We have U d phi this is always du by dxi phi dx, and this is true for all phi in C0 infinity. So this you can verify from appendix, and this integration by path is from Gauss divergence formula. And yeah, you can see in Ivan's page number 712. He has explained the notion. So now I will generalize this integration by part if we have a ck omega. So how we will how I will iterate the same integration by part k times, and I will get a different notion of integration by part, assuming that u is in ck omega. So let alpha be alpha 1, alpha 2. They all are I say this is a multi-index, and I use that 0 is also belongs to n. This is convention. I say alpha is a multi-index. I define, sorry, let always comes with B. Define order of alpha as this notation. I will denote this mod alpha as the order, and I will define it by taking all the component addition. And I denote the alpha u, where u is a function over omega, is d mod alpha u dx1. x1 has multi-index alpha 1, x2 has multi-index alpha 2, alpha, and this is in the same sense we have seen this in the Ph.D. Okay, so we have notation for multi-index. Now I will generalize the integration by part for CK functions. So let us see how I will do it. So we can generalize integration by part for a function which is in CK of omega. So by doing the successive integration by part, we obtain u d alpha phi over omega. This is -1 Oh, here we see that if my function u is in L1 log, so they are the locally integrable function, then star makes sense. So from here, the first idea of weak derivative appear, that we can give sense to this integral just assuming that u is a locally integrable function. So we can ask that whether if we assume only the locally integrability without assuming that function is ck, can we still have some other function here, let's say this is g, so that this star hold. So the purpose, does there exist a function such that for u in L1 log, we don't know the regularity yet. So we are just using the integrability property. Function v such that for this function u, we have integration u, this is same as and this equality hold for all phi in C infinity or C0 infinity omega. So people tries to find this kind of function, and later, so to give the sense of this integrability, the first we should know that if v is, it is enough to take v locally integrable. So the precise purpose is, does there a function v which is locally integrable so that this integrability makes sense, such that for our original function we have this equality. And you don't believe this is the definition of weak derivative. So I will give the precise definition. So assume that u is in locally integrable and alpha be a multi-index. Then a a function v, which is locally integrable on omega, we say is alpha at weak derivative. Of u. And we denote as d alpha u. This is just the notation is equal to v if it satisfies this integration by path. All compactly supported or for all test functions. So is the definition clear?
Hello.
Yeah.
I have some small doubt. In the last slide, you showed that that locally integrable function is it makes sense that star the equality.
Yeah.
Can you please give some idea how can you show that this makes sense actually?
Okay. So this integrable makes sense. Here phi is a compactly supported function. So it is zero outside some
Okay.
support.
Mhm.
So the only care you have here, so only you should care that we should not blow up in the support of phi.
Yeah.
So this means that the support of we should be integrable in the support of phi.
In the
That
support,
means
yeah.
that v is locally integrable.
Okay,
Because
fine.
support
Thank you.
support we are taking here is compact always. So do you
Yeah.
know that locally integrable means what?
Yeah.
Yeah, thanks. Okay, can we proceed? Okay.
Sure.
Yeah, thanks. So this definition is alpha at weak derivative. And I will some notation. So it is very hard in the beginning because you have a lot of notation to define. But if after this I will have a lot of theory. So the problem is yes.
Can you say something about without multi-index alpha? Yeah. Anything
Okay.
about doing it?
Okay. Okay. I have examples where I haven't used the multi-index alpha. So we will see the by example also. I will explain in the details.
Oh,
Yeah. So I will denote D0 U. Don't confuse here. This 0 is the multi-index. And this is U. And I will denote DU is du by dx1, du by dx2, du by dxn. For mod alpha is equal to 1. So, okay, let us see this the second one, because here I am using 1, but the 1 is not alpha here. Alpha is my multi-index, so alpha should be n tuple. So if my mod alpha is equal to 1 in Rn, so the first choice, let's say alpha can be 1, 0, 0. Sorry, n minus 1 times. So for this alpha, I calculated V from this weak derivative formulation, and I call that V as du by dx1. Now if alpha is 0, 1, 0, then I calculated my weak derivative by this star, and I call that du by dx2. So here each function is weak derivative, and I call this the collection of these functions, or the vector notation of this weak derivative. I call this as weak gradient. So you see that the weak derivative is just a function. But when I am using the weak gradient notion, it is a vector. And more specifically, it is just a partial derivative, first order partial derivative, nothing more. So don't confuse with here that I am using D1 as a multi-index. It is not a multi-index. So du I will always use as a weak gradient, and which means that I have a vector, because gradient has a notion with vector where each component is locally integrable function. And here dux1 is derived for alpha 1, 0, dux2 arrived for alpha 0, 1, 0, 0. So I hope this makes sense. Okay. So the first things comes to mind, that is this weak derivative, what we can say about the classical derivative and weak derivative. So we see here the classical derivative is always pointwise defined, but the weak derivative we define with the help of integrals. And here we can ignore the measure zero set because they are in L1 locally. So ignoring measure zero set doesn't affect the weak derivative, and it is a very big point. So ignoring some set in the classical derivative definition, it can make a big difference. But ignoring some measure zero set in the weak derivative definition doesn't change anything.
Can you just repeat what's the difference?
Can you please ask?
Can you just repeat what you just said? Once again?
Okay, so I will write it more clearly. So classical derivative, so this classical derivative definition, let's say Rn differential, this is defined pointwise. So for each point you have a derivative, and you say that derivative is a linear map satisfying some limit property. But in the weak derivative notion, you have this integration by path. And you know LP's L1, this is an equivalence class. So you say F is equal to G if Fx is equal to Gx almost everywhere. And what is almost everywhere? This means that Fx is equal to Gx outside some set A, where the measure of that set is 0. Outside this set A, fx is equal to gx with the measure of A is equal to 0. So this means that you can change the V on a measure 0 set. Then also this that the new V, suppose you change V prime, you define V prime V on omega minus A, and you give some other value W on A, where the measure of A is equal to 0. Then also this V prime satisfy this integration by part. But you see the V prime is V on omega minus A, and it take different value on a measure 0 set. So this means that V and V prime are almost everywhere equal. So that's what I'm saying. You can change the function value on a measure 0 set, and that function also satisfy this integration by part. So here I am saying that here what I am using is the LP space or L1 space property, that they are here the function are equivalence class. So you have a lot of representative, doesn't matter.
So the definition is almost everywhere.
Yeah. The definition is almost everywhere.
Okay, thank
Yeah. I think some remark. If U is in CK, then classical derivative up to order K are also weak derivative. This is from the definition of integration by part. And the second one is if U is 0 almost everywhere on open set omega, then all the weak derivative is 0 almost everywhere on omega. So these are just the consequence of the definition. You can check it. And
I have one question.
yeah.
So can we define directional derivatives of a function?
Here, so directional derivative, you have a limit.
What I'm asking is, will that become a dot product of this D1 U that you defined with the vector in the direction that you're taking?
So you in the classical derivative, you have
It's a dot product with a gradient, right?
yeah, you have a gradient vector, but here this is not a vector, so you cannot define a dot product. So I'm saying, yeah, I'm saying this weak derivative is just a function, a real valued function. Yeah, so
Which
you
is
don't,
almost everywhere defined.
yeah, which, so a function you cannot you cannot ask for any vector product. So to define dot product, you should have vector space structure, and you don't have do you understand?
No, what I'm asking is like this B1, that gradient is almost everywhere defined, right?
Yeah, which
Now,
weak gradient.
but at every point it's a vector, right? I mean, almost every point it's a vector, the gradient, right?
Almost every point. But do we have a vector space structure almost everywhere? We
But
say
it's in
for
Rn,
every
it's Rn, right?
For every
You are in
scalar,
Rn, right?
yeah, we are in Rn.
So what I'm asking is D1U, which you call the gradient. So almost
Okay, sorry, you are asking D1U.
yeah,
Okay, yeah.
D1U is almost everywhere defined, right?
Yeah, D1U is almost everywhere defined.
So now if I can ask about the directional derivative. Is there some notion like that? I'm new to
I
this, that's
haven't
what I'm
seen.
asking.
Yeah,
Okay.
I haven't seen any directional derivative. But in quasi-conformal, if this is classical, if we have a classical derivative, then we talk about the directional derivative. But I haven't seen here any notion of.
Okay.
Maybe we can, yeah. So the lemma 1, which I am going to. So I will prove that a weak alpha at derivative of u, if it exists, is uniquely defined up to a set of measure 0. This you can prove very easily. So let we have 2v and v tilde, two different weak derivative. So our weak derivatives of u, sorry, alpha. Then we know by definition u d alpha phi is same as -1 v phi, and this is also same as v tilde phi. So from these two, you can conclude that we have v minus v tilde phi is 0, and this is true for all phi compactly supported. And here I will use one fundamental result of calculus of variation, or you can see in any measure theory book that if f is locally integrable or L1, then integral f phi is equal to 0 for all phi which has compactly supported smooth. This implies that f is equal to 0 almost everywhere. So using this result, I conclude here that this is v minus v tilde is 0 almost everywhere. This means that v is same as v tilde almost everywhere. So it is uniquely defined up to a set of measure 0. Okay. Now we will see an example how to calculate a weak derivative. So let n is equal to 1. Here I am not using any multi-index because my dimension is 1. And omega is an open interval 0 to 2. And I consider the function u x in the range of 0 to 1 and 1 otherwise, or x greater than 1. So clearly you see that this is not continuous. So you cannot talk about differentiability. But I claim that the weak derivative exists here. So what is weak derivative? First order, first. given by, you try, so if suppose the weak derivative exists, then it satisfies that integration by part formula. So I will start by integration of by part. So I will compute this integral over my domain 0 to 2. So this says x in 0 to 1, and in between 1 to 2 we have 1. So here I will use the product rule of the integral, and we get that x phi x from 0 to 1 minus phi x 0 to 1, and by fundamental theorem we have this phi x from 1 to 2. So phi 1 minus integral 0 to 1 phi, and here I have phi 2 minus phi 1. So phi is a compactly supported function, so it should vanish at the boundary, and 2 is the boundary. So phi 2 will be 0. So this implies that we only get 0, 1 phi x dx. So by observing this, if we take that the function vx is equal to 1 in this interval and 0, then we see that this is satisfying the integration by part from here. Do you agree? Does anyone have doubt?
So it's basically kind of guessing the function, right?
Yeah.
So for higher dimension, how can we guess that such kind of function?
Sometimes it is very easy to calculate, and sometimes it is not. So if you are lucky, then you can get the function, but if not, then it is very difficult to find.
So even if we know that the function has the weak derivative, we are not able to calculate.
Yeah,
right?
we
In some
assume
case.
that there exists a locally integrable function, and we do all the calculation in the remaining term. Maybe you have seen this in distributional derivative. There also it is very hard to find for every distribution.
Okay.
Yeah.
Hello.
Yeah.
I have a question that mu has to be defined in 1 or not? This mu of x is not defined in 1.
Here.
And also this v of x is 0 over the interval 1 to 2, right?
I'm sorry, I am just using.
Okay. And one more question is that can we classify a function which have weak derivatives?
In Sobolev, no. So the solution of any PD has weak derivative.
Okay.
But in Sobolev, we have an extra condition that weak derivative exists, and weak derivative is also LP integrable. So in Sobolev class, every function has weak derivative, but with extra property.
Okay. But I
But
don't know about what is Sobolev class.
okay, no problem. Yeah, I will define
Okay.
the notion of Sobolev space definition. And there you can see that we are talking about only those functions which have weak derivative. And the weak derivative is also some P integrable.
Okay, thank you.
Yeah. I think we are running out of time. I have prepared a lot, but I haven't managed to finish it all. But still, okay, we can move further. I will define the definition of Sobolev space now. So it's the right time to define because we have the notion of weak derivative. Remember, Sobolev space is always defined on an open set. We are not, there is no notion of Sobolev space on a closed set. So assume omega subset of Rn open. The Sobolev space I denote this Sobolev space by WKP omega. This space consists of functions U which belongs to LP. So here my P is greater equal 1. I'm not talking about fractional Sobolev space. So there are some notion of fractional Sobolev space also where P is greater than 0, but here we are just in the LP case. And K is any integer, a positive integer. Then consists of function U which is LP integrable such that for every multi-index alpha with order less than equal to K, the weak derivative d alpha U exists and all these weak derivatives belongs to LP. So in the set form, how I can write, so I will denote WKP omega is the collection of all those LP integrable function such that for this K, the K is important here for all weak derivative up to order K. This means that d alpha U belongs to LP for all alpha with order less than K. So this is my set and this is WKP omega. And yeah. And I will equip this space with norm to make it Banach space. We will see why this norm is complete. If U is in WKP, we define the norm U WKP omega as all the weak derivative LP integrable norm. You take power P. And this is for when P is greater equal 1 less than infinity. And when P is infinity, I take the essential supremum norm. Yeah, I think I should stop now because, or anyone has some question, you can ask me now.
So you define Sobolev space for 1 less than equal to P less than infinity, right?
Yeah,
But so what is the definition of for that in that case omega wk infinity actually for p equal to infinity?
This one?
Yeah, I mean wk infinity.
Yeah.
In the definition you mentioned in the definition of Sobolev
Sorry.
space you mentioned that one less than. Okay, okay. Thank you.
Any other
One
question?
question.
Yeah.
One question. So you are taking an LP function. What I'm asking is, suppose it has a weak derivative, then does that guarantee that it should be in LP?
No.
Okay.
I have an example where the function has a weak derivative for a certain range, but for a certain range it doesn't belongs to LP.
So for any, I mean, is there any such domain so that this WKP is equal to precisely LP omega or something? I mean, this.
Sorry, can you please ask?
Yeah, this Sobolev space of order K. I mean, WKP is contained in LP, right?
Yes.
Yeah, I mean, is there any such domain omega so that these two sets are equal?
I don't think so, because in LP you don't have you don't require that the weak derivative also belongs to LP. But in Sobolev space, you want that weak derivative also belongs to LP. So there is some, I can modify your question a little bit. So if I drop the the P integral of the function, then then we have a homogeneous Sobolev space notion. And we have some space like balls with a smooth boundary or ellipsis boundary. Then we have WKP is same as LKP, the homogeneous Sobolev space. And it is proved by Koskela that if my domain is bounded and it satisfies P Poincare. So I will introduce what I mean by P Poincare inequality. Then the homogeneous Sobolev space is same as non-homogeneous Sobolev space, means this WKP, where you have.
So basically, in general, these two sets are, I mean, may not equal.
No, they cannot be. One is contained inside, but the other inequality is valid for very special case.
Okay.
Do we have any other question? Just check. Okay, so if not, let us thank the speaker. Thank you, Riddhi.